Assalamualaikum and salam sejahtera. My name is Syafiqah binti Sahmin and I would like to present my final year project on review on effect of plasticizer on ionic conductivity, morphology and molecular interaction of polymethyl methacrylate electrolyte. Allow me to begin my presentation with the content of my final year project. This is the main part that I would like to discuss further. Begin with the abstract of the review. The effect of plasticizer on ionic conductivity, morphology and molecular interaction of PMMA has been reviewed. Scanning electron microscope SEM used to analyze the morphology properties of the plasticized polymer electrolytes. Fourier transform infrared spectroscopy FTIR used to study the structure of the polymer and the interaction between electrolyte components of polymer host. SEM images reveal a porous surface structure of PMMA which allow ion conduction. FTIR spectra show the presence of adjacent metal group in polymer structure and the cation from ionic salt that will form bond with oxygen in PMMA. Due to the low ionic conductivity and brittle characteristic of PMMA, the addition of plasticizer has the ability to increase chain flexibility and ionic conductivity. I wanted to highlight the problem statement of the review. PMMA has been focused on among the other polymer hosts due to its amorphous nature, chemical stability and other properties. However, PMMA-based polymer electrolytes are brittle and have a low ionic conductivity at room temperature. So, PMMA-based polymer electrolytes with the addition of plasticizer have the ability to increase the flexibility and its ionic conductivity. There are three main objectives of the review. First, to review the effect of plasticizer on ionic conductivity of PMMA electrolytes. Second, to review morphology properties of the plasticized polymer electrolytes by using SEM. And third is to review the structure of the polymer and the interaction between electrolyte components and the polymer host using FTIR. Now I'm moving on to the literature review. First of all, we're back to the basic. What is a polymer electrolyte? Polymer electrolyte is an ion-conducting polymer matrix. Michael Faraday has discovered the solid electrolytes and created words like cation, anion, electron and electrolyte. Apart from that, the figure shows the chemical structure of methyl methacrylate and polymethyl methacrylate polymer. PMMA, also known as acrylic glass, which are transparent and a hard thermoplastic polymer that is usually used as shatterproof alternative for glass. There are three main classifications of polymer electrolytes. The first one is solid polymer electrolyte, which is formed by dissolving inorganic salt in functional polymers. The main advantages include mechanical strength, ease in thin film production, and ability to make good electrolyte. Second is gel polymer electrolyte, which combine the advantage of solid and liquid electrolytes. GPE has high ionic conductivity, good chemical and thermal stability, and etc. Last one is composite solid polymer electrolyte, which is formed when inorganic filler combined with polymer electrolyte. It is beneficial in solving the poor ionic conductivity of polymer electrolytes. Now, I will explain about the plasticizer. Plasticizer are polymers that create secondary bond with polymer chains and divide them apart, resulting in a soft and malleable polymer. Some examples of commonly used plasticizer are polyethylene glycol, propylene carbonate and ethylene carbonate. Plasticizer can be classified to primary and secondary plasticizer. The difference between both are primary can be employed on their own if they are compatible with the polymer but not for secondary. The mechanism involving the addition of plasticizer into the polymer matrix is called plasticization. Two ways to achieve plasticization are by external or internal. External plasticization done by physical mixing of plasticizer with polymer, or internal plasticization by chemical conjugation of plasticizer molecule. Now that we've been aware of the general or basic term, let's continue with the analysis and interpretation. Ionic conductivity of GPE is determined by two factors, carrier concentration and mobility. At the left side, the figure shows the typical impedance plot of 60 weight% of PMMA, 12.5 weight% of 2-plasticizer and 15 weight% of salt at room temperature. The spectra display two different patterns. One is semicircle at higher frequency, which related to bulk conduction process. The other one is linear at low frequency range, which related to blocking electrons. As the temperature increases, the conductivity of all samples also increase. This means polymer will expand more easily and increasing free volume. Then it will increase ion mobility, which helps in ion transport. The right side of figure shows the ionic conductivity as a function of lithium perchlorate salt in various solvents. As we can see, increasing the salt concentration up to 0.75 molar will enhance the ionic conductivity of all solutions, and vice versa. The dimethyl acetamide had the highest conductivity and it reached maximum at 0.75 molar. Increasing the salt concentration by more than 0.75 molar reduced the conductivity due to the ion pairing action. Next, I will explain the SEM analysis. In this slide, we have data from Faraday et al. 2018 and SEM images for GPE1 and GPE3. Based on the figure, pores were discovered on the surface of both samples due to the evaporation of the plasticizer. GPE1 have more porous morphology than GPE3 due to the increased amount of plasticizer. The connectivity of these holes in GPE3 is believed to provide better routes for salt ion transport in the polymer matrix. Continue with more finding of SEM analysis. The left side of SEM images obtained from Arya and Sharma 2017 shows the pure PMMA, PMMA with sodium perchlorate and PMMA with salt and plasticizer dimethyl formamide. All the images shows uniform morphology but different degrees of roughness. The surface properties and texture change significantly after the addition of plasticizer at figure C. Plasticization reduced the crystallinity of the polymer host, resulting in an increase in the overall amorphous fraction in the material. Last SEM analysis is from Shukla et al. 2014. The figure shows the pure PMMA and PMMA with salt film with different salt concentration. The smooth morphology indicates the amorphous nature of PMMA. The quick evaporation of the solvent causes tiny holes or several craters on the electrolyte surface. The addition of salt causes noticeable changes in the surface morphology of pure PMMA. As more salt added, the pore size grows larger and the polymer salt complex film has a uniform pore distribution. Moving on to the FTIR analysis, this slide illustrates the FTIR spectra from Sharma et al. 2012 for pure PMMA, lithium perchlorate salt and 3 samples. For the polymer electrolytes, the bond stretching frequency at 1715 has been changed to 1735 corresponding to C double bond O of PMMA. For bond stretching vibration of plasticizer has been assigned at frequencies 1737 and 1457. The peak of perchlorate anion at 968 found in polymer electrolytes suggests salt dissociation. As a result, the FTIR spectra analysis support the formation of polymer electrolytes.
Next slide is the FTIR analysis from Ramesh and Bing 2012. The figure shows the PMMA, PC 0% and PC 25%. All the peak obtained from the spectra has been listed as you can see in the slide. Variation and peak strength imply complexation happen in the polymer electrolytes. Last FTIR analysis by Faraday et al. 2018 shows the FTIR spectra for pure PMMA and GPE3. The peak obtained for PMMA, salt and plasticizer has been listed as shown in the slide. The presence of specific functional groups satisfy the requirement for an electrolyte system polymer host. To conclude the review, all the objective has been well achieved. When the amount of plasticizer increased, the surface morphology changed drastically. The connectivity of pores from SEM image provide better routes for ion transport in the polymer matrix. The presence of specific functional group detected by FTIR satisfies the requirement for electrolyte system polymer host.
Last but not least, this is the list of references used in my final year project. With that, my final year project presentation has come to the end. Thank you for listening.